We're talking about this idea of solving ordinary differential equations with power series. And it's a beautiful idea, because power series, you should really think of power series as being polynomials. And the idea is to say, okay, so there's this function we don't know, but we're going to think of it as this big infinite polynomial. In other words, we're going to make this assumption that our answer has the form y is this sum from 0 to infinity ck x. Okay, now, what we don't know are the c sub k's, the coefficients. And so now our work says, okay, how do we go about figuring these coefficients? So we prepare. It's a differential equation, which means there's derivatives involved. So we take derivatives. We take y prime, y double prime, so forth and so on. We say, all right, we have our basic building blocks all expressed in terms of series. And then we take these and we plug these into our differential equation. And so the hard part about the process, maybe I shouldn't say the hard part, but the bulk of the work happens in this step, step 3. This is the most important step. And what's happening here in step 3 is you're really saying, all right, plug y in as this series. And then you have all these pieces floating around. You have the powers are off, the starting points might be off, and you have to clean it up. And clean up means, okay, make the powers agree, make your starting points agree, and we have ways to do that. That's what we talked about previous lecture. We have ways to change our index. That helps fix the powers upstairs. We have ways to pull off the first terms. That helps make sure we start at all the same places. And so we put everything into one series. And once we finish that, we say, okay, now we have just a single series, and we look at the coefficients. And that helps us figure out what do the coefficients need to be. And so in particular, we can compare coefficients, and we can find recurrence relationships. And you'll notice recurrence relationships, that's an important idea, and it's a phrase you might see. So I want to make sure we spend some time talking about the idea here. But really, what's happening is once we have these recurrence relationships, it's how we find our coefficients. So now we're like, okay, great, we can get back and we get our answer. Because the only thing we didn't know about our answer was what were the coefficients. So what do we mean when we talk about recurrence relationships? Well, a recurrence basically says, I want to know what's going on right now, and I can figure it out based on what came before. So when we're talking about a recurrence relationship, what we're really talking about is that we can find our coefficient in terms of earlier coefficients. Pictorially, you should think of this picture. There's some relationship, and we plug in the previous coefficients. Now, usually we only need to plug in 1 or 2. But the point is we know everything that came before up to that point. We plug it in. Out comes our next coefficient we need. And we repeat and repeat and repeat. Now, sometimes we just say, all right, I just want to know the first 10 terms. That's enough for me to get a reasonable approximation. Sometimes it's possible to say, hey, we see a pattern emerging with these coefficients. And once we see a pattern emerging, we can say, all right, here's the general form. And then we can get nice expressions for the coefficients. In a few rare cases, we can get explicit answers for the solutions. All right. So in terms of what we hope you can do, we strongly want you to be able to do this process. So you should be very comfortable with this process. One other idea for today. We have these infinite sums. So you're adding infinitely many things together. There is a little bit of a catch. Does it make sense? In other words, if I add up infinitely many things, do I get something out at the end that's a reasonable thing? And sometimes yes, and sometimes no. And so the question is, well, when does it make sense? And we have a fancy way for saying that. Where do we converge? Okay. So there's this notion of a radius of convergence, but it says, in what range do we converge? So how do you find it? Well, there's lots of ways to find it. This goes back to Calculus 2, which of course we all have warm, fond memories of Calculus 2. And when we were talking about things like radius of convergence. And one of the ways we did it was something called the ratio test, where we looked at the ratio of consecutive terms. And looking at that ratio gives us sort of an idea of how fast the coefficients are growing. And that information, the speed at which the coefficients grow, gives us information about how far we can go and still converge. So that's where this fact comes from. So this is essentially the ratio test, in that it is a ratio test. So you look at the limit as n goes to infinity, the ratio of the current coefficient compared to the next coefficient. And if this limit exists, then that's the radius of convergence. Now, the limit might be infinity. That's the ideal scenario. That means we converge everywhere. Might be a finite number, and that's okay. That just means I converge in some small interval. It might be 0, in which case it means your answer is basically worthless. But hopefully we don't encounter that situation. So keep that in mind. And there's this comment here, which we might come back and see this comment later on. It says, because these series solutions sometimes have constraints where they can't converge very far, it's possible that a series solution only works for a small piece, whereas other solutions can actually be pushed further. Now, I know that's a vague statement, but perhaps, like I said, we'll have a chance to revisit this statement later on today. Are there any questions before we get into our first, hopefully not last, example of the day? Okay, then let's begin. So, this doesn't look so bad. Solve x plus 4y prime plus 3y equals 0 by use of a power series. And determine the radius of convergence of the answer and compare the answer to what can be found by other methods. So there's actually a lot going on here. There's the solve, so we're going to work on that. There's the radius of convergence. We'll work on that at some point. And then there's the comparing it with other methods. So there's like 3 small problems in this one big problem. So it's going to take us some time to work through it all. But that's okay. We're very patient people. We're very patient people. That's what makes us great engineers. Let's start with the solve. Definitely we can't talk about radius of convergence until we get to solve. Not yet. Next time we can. But today we need to solve first. Okay, so how does the process work? Well, we know what our answer should look like. It should look like a series. Sum k equals 0 to infinity, c sub k, x to the k. If you don't like k, you can use n, l, m, any symbol. I use k. It's just a default for me. What else do we need to have? Y prime, because there's a y prime here. So what is y prime? Okay, so k comes down. ck x to the k minus 1. You'll notice I pause here. I haven't written this yet. Now, could we write k equals 0? Absolutely. Yes, absolutely we could. But what else could we write here? Yeah, because k equals 0, basically the term goes away. So we'll just save ourselves, make it k equals 1. We either have to do this idea now or do it later. Let's just do it now. And we don't need any more derivatives because we only have the function in the first derivative. So that's great. So where to from here? Well, we have our function. Plug it in for y. We have our derivative. Plug in for the derivative. And that's what we're going to do. So see, these parts are almost automatic. It's like we know what the answer looks like. We write down our derivatives. We plug it in. Very little thought has to go in at the start. So x plus 4, y prime, sum k equals 1 to infinity, k, c sub k, x to k minus 1, plus 3 times y, sum k equals 0 to infinity, c sub k, x to the k. All that will equal 0. All right. So up to this stage, it should be fairly mechanical. No thought needs to come in. Here's where thought has to start entering in. We need to take this left-hand side and write it as a single sum. One sum to rule them all. One sum to find them. One sum to bring them all. And in the light of differential equations, bind them, right? Right? Okay, good. So how do we do it? How do we do it? Sorry, what?
Equal starting points.
Okay, we got to make our starting points line up. Yeah, that's going to be something. Exponents first. Okay. Distribute. Okay. There's all these fun things to start with, right? I would recommend distributing out first. Worry about exponents before you worry about starting points. Because when you change exponents, you also change starting points. So you don't want to have to redo this change starting points multiple times. And here's something I would recommend. It may not seem the most intuitive thing. Sort of like our idea says, hey, let's put the x plus 4 inside here. I would recommend doing sort of the opposite. Multiply the sum out. Now, you get to the same place, but I think it's a little bit easier to follow the thought process if you do that. So we have x times our sum, k equals 1 to infinity, k, ck, x to the k minus 1, plus 4, same sum, 1 to infinity, k, ck, x to k minus 1, and then we have the other piece on the end. All right. What's next? Okay. Now move the pieces inside. So we're going to take those sort of leading coefficients and we'll just gently nudge them in. So what does our first sum become? 1 to infinity of? K, c sub k, x to the k. You've added an x. All right. The second sum. What happens in that one? There's a 4 that comes in. 4k, ck, x to k minus 1. Last sum. No big surprise on that one. 3ck, x to the k. All right. So this is actually pretty good. Now, looking at these sums, I would say that the first sum, we look at that and say, hey, we're pretty happy there with that sum. And why are we happy? Well, there's a smiling face. That's why we're happy. But no, because it's x to the k. That's what we want. Last sum, again, we're happy. Middle sum. Well, I don't want to say we're frowning, but we're like, The difference with the middle sum is that our exponent's not quite right. So how do we fix that? Okay, someone said shift to a different frame of reference, which is actually a nice way to think about it. You can call it reindexing. You can think of it as like, oh, it's our substitution. We're just changing our names. So, what do you want to call our new index? L? Okay. I can already see I'm starting to have an influence. I hope it's a positive influence. All right, L. And we'll call that be k minus 1. Okay, so now let's think about what we have. Now, the ones on the end are fine. But just so everybody's happy, I'm going to write these in terms of L as well. So just everything has the same index symbol. That just makes it easier for us to see, oh, things work as they do. And it's fine to do it individually. So the first sum pretty much is just copying. Only thing that happens is instead of k's, I'm putting l's. It's still the same sum because L is an index. So it doesn't matter what I call the index. If I change the index to another name, it's still the same sum. Okay, so that's not so hard. The second one is one where we have to say, Okay, so let's start right at the very beginning. We used to start at k equals 1. Where do we start with L? 0. We used to stop at infinity. Where do we stop now? Yeah, infinity minus 1, but that's infinity. 4, what does the k become? Yeah, so you can solve for k. It's L plus 1. So 4 times L plus 1. The c sub k, Cl plus 1. And x to the k minus 1, well, that's our choice, was to make it x to the L. So that's the middle sum. That's the one where we actually have to think. The last sum is not any thinking. It's just a matter of rewriting it using our new symbol. So L equals 0 to infinity, 3Cl x to the L. And all this equals 0. All right, good. Now, are we ready to put these together? And why not? Yeah, they don't start at the same place. You look at, see, the nice thing is they all have the x to L, x to L, x to L. I was like, yes, good, we like that. The problem is, where do you start? Well, at one place we start at 1. 2 places we start at 0. So where should we be starting? Well, we should start at 1. So it's like, what's the first place where they all agree that it's like, I cover that? They all have a 1 in it. But only 2 of them have 0 in it. So what we'll do is we're gonna pull off enough terms so everything starts at 1. So we have our sum. Our first sum, don't have to do anything. It already starts at 1. L, C sub L, x to the L. The next sum, we have to pull off the term corresponding to L equals 0. For the term L equals 0, what do you have? What does this become? Yeah, so 0 plus 1 is 1. So 4 times 1 times C1. So this is the L equals 0 piece. And then we have the rest of it. So 1 to infinity, 4L plus 1, Cl plus 1, x to the L. So we pull off the first term. Okay, do the same thing here. If we pull off the first term, what do we have? C0. Yeah. This is, of course, one of our cases where the first term is the corresponding to 0. All right. So again, that's the L equals 0 case. And then the rest of the sum. 1 to infinity, 3 C sub L x to the L equals 0. Oh, we're barely squeezing it in, but okay. I'll claim we made it. Now we combine. First off, let's combine the things that didn't end up in the sum. So What didn't end up in our sum? Yeah, 4C1, 3C0. Essentially, those are our constant terms. Okay, so we have 4C1 plus 3C0 plus, and now the three sums, we combine them together, plus the sum, starting 1 to infinity of, and I'm going to group the coefficients because everything has an x to the L. So from the first term, L, C sub L. Next one, 4, L plus 1, C, L plus 1. Last term, 3, C sub L. And all this equals 0. All right. Whew. Catch our breath. If we are going through the process, we've now successfully done step 3, which was combine everything into a series, one series. That's what we've done. So this is the hard part. Well, hard part number 1. Now we come to and say, all right, what we've really done is we've grouped our coefficients together, and we're going to say, what do we know about these coefficients? So, for example, what's true about 4C1 plus 3C0? Well, that's the constant term on the left-hand side. What's the constant term on the right-hand side? 0. So what's true about this? It has to be 0. What about this term? That's the coefficient for x to the L. On the left-hand side, what's the coefficient for x to the L on the right-hand side? 0. So what's true about this? It has to equal 0. So we now have the following. 4 times C1 plus 3 times C0 has to equal 0. And then we have this. So let's group. Let's rewrite this. I want to just make one quick note. We actually can combine a few pieces together. Do you see how these both terms here have a C sub L? Let's just sort of put those together. So we get 4 times L plus 1, C L plus 1. That's the middle term. Plus, then we have a 3C sub L and an L C sub L. So we write that as 3 plus L C sub L equals 0. Now, this last equation, when is this true? For which values of L is it true? Well, if you're wondering, where does it come from? It comes from this sum. Where does our sum start? It starts at 1. So this is true for L greater than or equal to 1. Okay. Or is it? Ha ha ha. Let's just take a look at this. Say, these are kind of similar to each other. What happens when you plug in L equals 0 into this expression? You get 4C1, 3C0. So actually we can just say, lo and behold, we have the following. 4L plus 1, CL plus 1, plus 3 plus L, CL equals 0. This is for all L greater than or equal to 0. So in other words, you can combine these two into 1. Now that won't always happen, but sometimes it does. We know it can sometimes happen because it did. All right, good. Now, this is good progress for us. This part right here is what we would call our recurrence relationship. So if it was asking for, hey, what's your recurrence relationship? It's going to come from this piece. Now, probably we should do a little bit of work on it. I know it looks like I missed the I. There's a very thin I that you can't see there. Okay. We are going to go a little bit further with this one. Any questions on what we've done so far? All right. So, recapping what we have. We said that our solution to our differential equation has to form sum k equals 0 to infinity, c sub k, x to the k. And we have our recurrence relationship, this one right here. Now, I'm going to solve for CL plus 1. Now, you might say, well, why solve for CL plus 1 instead of CL? The key is I want to solve for the largest subscript. So L plus 1 comes later. So in other words, I can solve for L plus 1 in terms of the one that came before. And CL plus 1 is equal to, so I would move the other piece to the other side, subtraction, and divide. So minus 3 plus L over 4 times L plus 1. I can write that as 1 plus L. And C sub L. All right. So we're going to use this to start to dig into what is y. We're really going to get into it. So let's start with our coefficients. C0. What can we say about C0? Well, I'll just say the following. It's a free choice. And what happens is when you're dealing with a differential equation, you have some constants involved in your answer. You're like, I get to pick some choices. And what you should think of as C0, you should think of this as being what happens to your answer at y of 0. Because oftentimes when you have a differential equation, you say, okay, I have this expression. In our case, if you go back to the original statement of the problem, we had our expression x plus 4y prime plus 3y equals 0. And then an initial condition would be y of 0 equals something. Well, the y of 0 would be your C0. And it's your choice. Okay, so the rest of the coefficients, we don't get a choice. It'll be completely determined. So let's talk about C1. So how can we figure out C1?
Put it in terms of C0.
Put it in terms of C0. This is where the recurrence relationship comes in. So we're going to come to our relationship, and we're going to put in L equals 0. So if I plug in L equals 0 into this relationship, what comes out? Negative 3 over 4 times 1, C0. Yes? Okay. How about C2? Well, C2, we can come to our recurrence relationship and plug in L equals 1. If we plug in L equals 1, what do we see here? Negative 4 over, well, I know people are like 8, but let's write it as 4 times 2. And you're probably like, oh, Steve, you don't even know what 4 times 2 is? And they let you teach the class? But oftentimes, there's a danger in simplifying. If you're looking for patterns, it's better to not simplify right away. Rather, let things sort of accumulate and see the general form. Because if you simplify too early, it can be a little bit confusing as to see where things are coming from. Do we know what C1 is? Yeah, it's right up here. So notice there's a negative and a negative, which makes it positive. Upstairs 4 times 3. Downstairs 4 squared times 2 times 1. Okay, C3. What will that be? -5 upstairs, downstairs. 4 times 3 and C2. Okay, so we know it's C2. That's the previous line. Positive now becomes negative. Upstairs. 5 times 4 times 3. Downstairs. 4 cubed and 3, 2, 1. C4. Okay, so negative. Upstairs will be 6. Downstairs will be 4 times 4. C3. Well, 2 negatives makes positive. 6 times 5 times 4 times 3. Then we have a 4 to the 4th. A 4, 3, 2, 1. C0. Do you see a pattern yet? Okay, the denominator has like a factorial going. That's good. Anything else? Pretty close to the numerator having a factorial. Someone else said, hey, you're flipping signs. That's a good thing. And so if we put it together, we could say the following. So say, aha, mwahaha, C sub k, we see a pattern. Upstairs, well, we'd start, see, if it's 4, we start at 6. Oh, first off, let's get the alternating thing in. When it's even, it's positive. When it's odd, it's negative. So that would be -1 to the k. Upstairs, well, at 4 we start at 6, at 3 we start at 5, at 2 we start with 4. So it starts at +2, and it keeps going down, and it stops at 3. Downstairs, well, we have powers of 4, and that's 4 to the k. So like C4, 4 to the 4th, C3, 4 cubed, C2, 4 squared. And in case you're getting nervous, like, are we going to have to be expected to do all of this? Usually, we'd be pretty happy if you got to there. But we want to show you the ideas. Want to let you see more. Can we simplify? Yes, good. I like that attitude. How does this simplify? The k dot dot 3 on the top and the bottom cancel out. So there's -1 to the k and 4 to the k. You can even combine those. So you get -1/4 to the k. And we end up with k plus 2 times k plus 1 over 2. And I forgot one thing. What did I forget? C0. Okay, so here we go. Here we go. We can now say that our answer has the form sum k equals 0 to infinity of, and I'm going to replace our coefficient by, we know what our coefficient looks like now, -1/4 to the k, k plus 2 times k plus 1 over 2, C0, x to the k. But we can do some things. We can pull out constants. What constants do we have? C0. We can even do the over 2. Can you pull out the k plus 2? Can that factor out? No. Anything that involves k changes. It changes with k. So anything with k can't come out of the sum. It has to stay inside. But anything without k can. So we can think of this as C0 over 2 times the sum, k equals 0 to infinity, of -1/4 to the k, k plus 2, k plus 1, x to the k. And C0 over 2 Well, we can give this a different name. We can just call this C. Just some arbitrary constant that we get to pick. Okay, so there we go. There's our beautiful answer. Isn't it lovely? So this is like going above and beyond. And now we're done with part one of the problem. You might say, what? What was part one of the problem? Part one of the problem. Solve this by use of power series. And we did it. There it is. That's the solution. Part two. Radius of convergence. Now, you might say, we're going to be here a while, aren't we? Not with number two. Number two is going to be quick. If anything, number two will take a fraction of the amount of work that we've put in. Because actually, we get to use a lot of our work. We get to recycle. Remember that we have this fact that says, look at the ratio of consecutive coefficients and ask what happens to it. So you have, think of it as one coefficient compared to the next coefficient. Now, is there any expression which involves one coefficient and the next coefficient that we've seen? Anything at all? Anything that one. That one right there. In other words, the recurrence relationship. Okay, so what we're going to do, so keep in mind, I want to be really clear, we're going to look at one coefficient versus the next. So we're going to look at C sub L divided by CL plus 1. So I'm just going to come to here, and I say, okay, divide the CL plus 1 across and move this back over. So that would be 4 times 1 plus L over negative 3 plus L. Yes? Okay, so next thing, this has an absolute value. All right, put an absolute value here. How does it change the right-hand side? Get rid of the negative. Now, the other thing says, let this go to infinity. So, in this case, it's L, not N, but let L go to infinity. What does this approach? So, this goes to 4. Because if you think about it, ignore the 4 for a second, L plus 1 over L plus 3, you look at, these are polynomials to the same degree, you look at the leading coefficients. So, what is this number 4? That's our radius of convergence. So in some sense, when you have that recursion, especially if it's a first order differential equation, finding the radius of convergence is a freebie. It pops out. Okay. Oh, that was good. We deserved a break after part 1 of this problem. Okay. Are we ready for part 3? No? No, it is not. But we should still do it. Okay. Compare the answer to what we can find by other methods. So now we're going to do this problem without using series. And I know what you're thinking. Are you serious about that? Yes. We're totally. All right. X plus 4, y prime plus 3y equals 0. We're going to solve this differential equation without doing series. How can we do it? Linear first order. Anything else we can do? It's separable. You have a preference? Separable? I like separable. Separable oftentimes is a little bit shorter than linear first order. Make sure you can do both because there is an exam coming up. Okay, so separable, the idea is you separate. So this is really x plus 4, y prime, think about it as dy dx, equals minus 3y. And then, we separate. So I'm going to put the y term across. I move the x plus 4 and the dx across. dy over y is minus 3 dx over x plus 4. Yes? This is, they're starting to come back. It's like, oh yeah, we did this stuff. I remember that. The good old days. The good old days. Now what? Integrate. Okay, integral of dy over y. Natural log y. Equals, on the other side. Negative 3 is a constant. Natural log x plus 4. Anything else? Plus c. Oh, I'm glad you're all like, yes, plus c. Oh. All right. But I want y. How do we get just y? E to both sides. So we get y equals what? Will be some constant. What happens to this negative 3? Let's talk about that first. You can think of it as going in as an exponent. So it's like x plus 4 to the negative 3 power. So you can think of it as x plus 4 to the minus 3. Or we have y as some constant over x plus 4 cubed. Okay, so that's that solution. Now, versus, and I'm just going to copy this one down. Some constant c, some k equals 0 to infinity, negative 1/4 to the k plus 2, k plus 1, x to the k. Okay. Well, what do you think? Are these the same? They both have c. I like that. Okay. They both have a symbol in common. And they both have x's and 4s. They must be the same. Oh, wait, there's no 3 on that one. What? Okay, so are they the same? It's not so clear, is it? Let's take a minute to convince ourselves that they're the same. 1 over x plus 4. Does it vaguely remind you of any kind of series that we do know? Put back, your Calc 2 hats. Like, okay, I'm wearing my Calc 2 hat. 1 plus x the alpha. Oh my gosh, you really want to go there. Wow. Interesting. I was going to do geometric, but we could do that. So do you want to start geometric, or do you want to go all the way and go straight to binomial? Geometric? Okay. I like geometric. Binomial is actually fun. The answer is much faster with binomial. So let's go to geometric. Just so we can have the experience. We deserve the fun. Now remember that geometric says 1 over 1 minus what's in the box is the sum, k equals 0 to infinity, of that box to the k power. Which raises the eternal question. What's in the box? What's in the box? Okay, so that's what we're going to focus on. So we're going to start with our sum. Well, actually, we're not going to start right with our sum. 1 over 4 plus x. Now, we want to make this look like that. And you're probably thinking, we're a long ways. But we'll chip away. Definitely the top is good. That 4, I don't like it. I want to make it a 1. There's a lot of ways to make it a 1. Does anyone know a good way to make it a 1? If we split 4 up as 1 plus 3, that can be a little dangerous. Because then we have to deal with the plus 3. So there's this really cool technology that's come out recently called factor out of 4. It's state of the art. So I'm going to factor 4 out. So it's 1 plus x over 4. Okay, the 1/4 is a constant. I am fine with constants. I work with them all the time. But there's a plus here. I want a minus. What can we do? Subtract a negative. So 1/4, 1 over 1 minus x over 4. And now we're ready to answer the question. What's in the box? The answer is negative x over 4. So we end up with 1/4 in front, sum, k equals 0 to infinity of minus x over 4 to the k power, which you can think of this as 1/4 sum k equals 0 to infinity minus 1/4 to the k x to the k. Sorry, I'm just running out of space there. All right. Now, that's 1 over 4 plus x, which is like 1 over x plus 4. And in the interest of time, because we do want to finish before class expires, we're going to do something to make it look like x plus 4 cubed. Now, the thing we don't want to do is multiply a series by itself, because that means we have to work. So we start thinking, what are things we can do to x plus 4 to make it look more like x plus 4 cubed? And the answer is, we're going to take a derivative. What's the derivative of 1 over x plus 4? Negative 1 over x plus 4 squared. See, we're already closer. Okay, if I take derivative here, take derivative there. 1/4 sum k equals 0 to infinity minus 1/4 to the k x to k minus 1. Now what? Yeah, it's a trick so nice, we'll do it twice. What's the derivative of negative 1 over x plus 4 squared? 2 over x plus 4 cubed equals 1/4 sum k equals 0 to infinity minus 1/4 to the k minus 1, x to the power k minus 2. Now, a couple of things, and we'll start to see, aha, they really are the same. I left it at 0, but where can I actually start my sum here? 2. Because the first two terms are just going to disappear. Let's fix this so this becomes like x to a power. So again, re-indexing, we'll let k minus 2 equal L. So this would become 1/4 sum 0 to infinity of minus 1/4 to the k would be L plus 2. And then we'd have not enough space to write down what I need. K plus 2, k plus 1, L plus 1, sorry. L plus 1, L plus 2, x to the L. We're getting close. This negative 1/4 to the L plus 2, I can think of it as negative 1/4 to the L times negative 1/4 squared. So we can pull out the negative 1/4 squared. This should give us 1 over 64. Sum L equals 0 to infinity of negative 1/4 to the L, L plus 2, L plus 1, x to the L. And that all equals 2. So the punchline here, 1 over x plus 4 cubed, is some constant multiple, which, remember, we have constants, so we're okay. Hold on, there's a punchline here. You don't want to leave before you hear the punchline. So, that looks amazingly like that sum. So, are these the same? And why not? Whoa, I know, you're like, I told you, you want to hear the punchline. No, constant, I don't care about constants. Constants are constants. When is this solution valid? C over x plus 4 cubed. Everything above negative 4. You can't go below negative 4. You can't get past an asymptote. An asymptote is a boundary you can't go past. But other than that, we're fine. When is this solution valid? -4 up to +4. Where are these numbers coming from? Radius of convergence. So this is that statement I said, hey, we'll come back to it. And we did. The series solutions might only work for a small part, whereas other solutions might work for a larger part. But at least locally, these are the same near zero. All right, we did it. We finished one problem. Woohoo! See you next time.